Okay, hello. There's Lunar. All right. Nice. There's Lunar. There's Gabriella. There is Sydney. There is Effie. There is Jocelyn. There is Melanie. There is Mohammed and me, strangely. Oh, and now there's Jean. Sorry. Okay. Let's just get going. Hold on. Um, there's Angelina for where's it? Okay. There's Melanie for the double. Teresa for the Teresa. Mohammed for the double. Nadine for the where's Nadine? God.
Morning.
Oh, that was voice. Was that Mohammed? That's
Yes,
awesome.
sir.
Yes, sir. Oh my God, sir. You know, in the South, when they call a teacher sir, it means they've cheated. In the South, though, and it's not true. I love sir. No, I don't. I have mixed feelings. Okay, Sydney, good morning for the double and and Jocelyn, good morning for the double, triple. Double. Good morning, Gabriella, for the double. And also, I know some of you, including Gabriella, were here super early. I appreciate it. Totally noted. I couldn't. Okay, Christopher, good morning. Jean, good morning for the double. Also here very early. Good morning, Norma. And Sibo's here. All right. We're gonna get rolling. So some logistics. We're almost at a holiday. I know it's that time of crazy year. So, oh, wait. So one of you noted that I should adjust the um the second to last homework. Oh, people start. One of you helpfully pointed out that it would be nice if I adjusted the second to last homework due date, and I did, but stupidly. So this is my clarification, and I did in the classroom. I adjusted. I guess it's homework 8, but I made it due this Wednesday, which I just realized like an hour ago. Of course, that makes no sense. You don't have school this Wednesday. I don't think. Wait, actually, hang on. Wait a minute. Do we have school this Wednesday? We do. We do.
Yeah.
Yeah, we do.
I'm so stupid. Okay, we do. Okay, good. Where's my head? Okay, well, nonetheless, I had a momentary lapse of craziness. So I adjusted it again anyway. I'm confusing our school with my son's school. So I adjusted it again anyway. I made it due, I believe you'll find, because I want to talk more. I'm just going to start talking about work and energy today. Um, so good or bad, I adjusted it again and made it due on Monday, and then the gravity homework is due a week, I think. I don't now I'm getting myself good. Just check a Google Classroom. I think you'll find that everything shifted one last time, and I think that will be the last time because then we're into December, blah blah blah, and that's the end of the homeworks. But if I contradicted myself, if I somehow made them both due on the same day or something, let me know. You're welcome. You're welcome.
I
Okay.
think they're good.
Thank you, Gabriella. Okay, thank you. And that's voice and multiplayer co-op. Thank you. And please I owe you points. Anyway, submit the points for that. Okay. Now, also, speaking of that too, I'll just say this quickly to get out of the way. Now, many of you will find that you have gotten your exam back. But many of you will find you have not. It's totally not personal. It's like alphabetical by first. It has nothing to do with your performance in the class, whether you've gotten it back or not. In some cases, you might have gotten a note from me saying, wait, I'm finally up to your exam, but I can't comment on it because it's not a PDF or whatever. Please don't take that as me. Just please, if you see that note that I need a PDF, that's just all it means. I just can't. It means I know you're on time. Even if you resubmitted, Google Classroom says you're late. Don't worry. I know you're not. Um, but it needs to be a PDF for me to be able to. Anyway, so I don't want to get all bogged down in that now, but hopefully those of you who have gotten your exams back do see that hopefully you got a lot of feedback, and the whole idea is like so that you'll know exactly what to do for the final. If you haven't gotten back, you'll get it soon. You will. And you'll certainly get it in time to fix for the final. But more than that, and I'll move on in a second, more than that, whether you've gotten it back or not, the idea is that you certainly like once you go through the comments, like they're tight, you absolutely should be able to see in doc comments. That's why it takes me so long. So if you can't see them, that means open it in a new tab, or open directly in Google Docs or whatever. But there certainly is feedback that's meant to help you improve for the final. So that also means number one, and again, I know this doesn't apply to everybody yet, but if you haven't gotten an exam, you'll probably get it in the middle of break like soon. So when you get the exam, like obviously go through the feedback. Don't freak out about the score. We'll talk about the scores like when everybody has one, but the scores are always a little bit jostly on the midterm of Physics 203. Just worry about the feedback at first. Know that once we get back from Thanksgiving, you absolutely, any one of you that wants to um, discuss the feedback or what you need to do to improve for the final, like we'll make a phone appointment or a Zoom appointment or an office appointment if you can come on Tuesdays. I will do that. It may not be before Thanksgiving with all of you, but like anybody who needs that, wants that, absolutely. That's okay. And obviously also if you just want to like talk about like, wait, is it still possible for me to do okay in this course? And the answer to almost all of you is yes. Like we'll get to that, but don't the scores on the midterms are always a little scary to people. So don't be scared. Just take the feedback and talk to me if you want a checkpoint of where. Anyway, I'm going to move on. But so I think this class is doing very well. Let me just put it that way. Okay. Everything I've seen so far, you guys are hanging in. You're doing what you're supposed to do. It will come out in the wash if you just keep hanging on. And I know it's been frustrating to wait this long for that. But the point is for you to get feedback in time to know what to do for the final. And that you will have. Okay. So wait, I'm just looking in the good morning, Sinead. Awesome. Okay, so now I'm going to move on to the concept of work, which you had to do one assignment about. Oh, and I apologize also. I know in the assignment it makes references to textbooks that like no longer are required for this course. I apologize for that. Obviously, you just find information wherever you want to find it. Um, but now I'm going to explain the information that, okay. The goal of today is to get to these equations that are written on the board here. Um, that's the goal. So, okay. Okay. Um, put perspective on what's happening now. The whole goal of physics is always still predict where something is going to be when. The original premise is that if you know the acceleration of a point of mass at a point in space, in a point of time, if you know the instantaneous acceleration, then you can predict the velocity in the future or you can predict the trends in the velocity and therefore infer displacement per time. So you can predict where an object is going to be at some time point in the future. Or if you're a forensic science student, you can solve crimes by retrodicting where an object was at some point in time. But the whole like premise was in order to predict the future or analyze the past, you need to know the acceleration of the object right now, right here, right? So it was all about acceleration, like for like the first month and a half or whatever. Then we backed up and said, well, how do we ever know the acceleration of an object? We look at all the forces acting on that object at a point in space and a point in time. So we drew these free body diagrams with a bunch of arrows acting on a dot in a point in space and a point in time. And those arrows led us to the instantaneous acceleration, which is to say the second derivative of position with respect to time. The whole picture of A and F net equals ma, that whole Newtonian picture is a very, ultimately it's a calculus picture because we're analyzing what's happening like in the limit as we shrink time to zero, time intervals to zero, right? And it's not a coincidence that the man who's thinking of this law, F net equals ma, is the same man, is the same person who develops this whole idea of derivatives, slopes of functions taken to the limit as time intervals are shrunk to zero, right? In other words, what I'm trying to emphasize right now is that the whole way that we've been looking at physics until now has been like pixel by pixel. We analyze a pixel of space and time and the pixel of mass that is in that pixel of space and time. And we believe that by scrutinizing that one frame, we can infer the whole movie. That is a derivative. Like, even if you're not constantly doing like product rule or quotient rule or like all of these mechanics that you learned in a calculus class, the conceptual approach is totally the conceptual approach of differential calculus. It's thinking of the world in terms of derivatives and believing that if we know something about the derivative or the second derivative, i.e., acceleration, then we can infer the whole function of position with respect to time. Okay, so the big picture, when you go dot by dot by dot through the world, thinking that by putting together the dots you can have the whole movie of the world, that is believing that derivatives can tell you something about larger functions. Okay, now we're going to shift our attention. Now, instead of, or now you already did with the homework you already did, but and also in the lab, now we're shifting to not what are all the forces acting on a point in space and time, but rather what is the effect, what is the consequence of a force acting throughout a finite interval or a finite region of space or ultimately time, right? In other words, so really what's happening here is we're shifting our attention from a derivative way of looking at the world to an integral way of looking at the world. Now, and okay, now I'm not going to get like, so Wednesday, I'm going to talk, this Wednesday when we do have school, I will talk in detail about the integral of calculus, right? That's really what, but I want to build to that today and introduce this idea. As it says on the front sheet. Here, actually, sorry. I'll be a little bit more rigorous. Okay. So I want to be careful here. So we're getting to this concept of work. Okay. I want to define, I'm not, what I'm defining right now, and it's a definition. So it's a starting point. Like I'm not proving something and I'm not basing something on something I've said before. I'm literally introducing like a new concept. And the concept is work, the physics concept, WRK. And I'm specifically right now defining a small but finite amount of work. You might even put in your notes and you could submit for points. If ever in math or physics we use the triangle, the capital Greek letter delta, I mean you've seen it a million times in math before, but what you I'm actually going to say it really quick. Okay, if you have any variables, call it Z. I'm intentionally using the letter Z to mean like it could stand for anything. It could be X, it could be Y, it could be Q. Like any variable, right? When you say delta Z in math class or science class, what you actually mean, delta means difference. Delta Z means a small, but it could be small, it often is small, but nonetheless finite difference between two values of the variable z, i.e., z2 minus z1, right? Like you know from math, from calculus, like when you say slope, slope is delta y over delta x. And what is delta y? It means rise, and delta x means run, means y2 minus y1 over x2 minus x1. The delta is connoting, is telling you that there is some sort of measurable, like noticeable, finite distinction between the two values of that variable that you're measuring. So from now, okay, so I'm good. So basically, I'm saying delta is what we use when we mean possibly very, very small, but nonetheless finite difference between two values. When we say delta, that's what we mean. So I'm now defining a small amount of work. I'm saying a small but finite amount of work is going to be defined in English as the impact of force throughout or like over space. Like in English, what it means to do work is to push or pull something through space, through a displacement. Specifically, technically, a small but finite amount of work will be how hard you pushed something or pulled something through a possibly small but nonetheless finite difference between two positions of space. So from now on, oh, sorry. So I'm going to go on, but I'm trying to make this distinction that like this is like a shift in the way that we're thinking about the world. We were thinking when we talk about force up until now, we're always picturing it, like I said before, as in terms of pixels. Like up until now, whenever you push or pull something, you analyze like what's happening at that moment at a certain place. Now we're saying, but what if you like push something for a while, like through a space? What if you push a block across a table? Or push as the homework, push, a boulder up a ramp. Like, what is the accumulated consequence of interacting with another object throughout a finite interval of space? That's what we're asking when we ask the question of work. So it's a product from now. Like if you multiply a Newton by a meter, you get what we're going to now from now on call a joule. And indeed, it's the same joule that you know from chemistry. It's not a coincidence. We'll get to that soon. Or I mean, you may already know, but it's that same joule. Um, but notice it's a product. Like the whole idea is the harder you push something, the more work you're doing, and the more effect, the more result that like yields, the more work you're doing. So work, you might say work is like interaction. To do work on another object is to interact with it and produce a result, a change in that object. What kind of change? A change in that object's position. Uh, but so it's a product, it's multiplication. Notice one of the features of multiplication is that if either term goes up, the whole product goes up, okay? But also specifically, if either term is zero, then the whole product is zero. You could push something as I could push the wall as hard as I want. That's a force. I could push for a long time. That's a force I'm exerting on the wall. But if the wall doesn't move, I haven't done any work on the wall. Okay? Um, um, okay, so in really like general terms, for a small but finite amount, if you exert a force on something through a small but finite amount of displacement, then you've done a small but finite amount of work on that thing. That's in general terms. Um, and notice I'm restricting myself all of today. I'm restricting myself to small but finite. And all of today we're dealing with small but finite. Um, that's why if you're asking, well, okay, I'll just say, I guess. Excuse me. Oh my God. Sorry. Oh my God. Sorry. Okay, just to be clear, why I keep sorry. Sorry. Could the sentence be continued to include per unit time? Wait, that's a great question. Hold on, Mohammed. Great question. Uh the sentence. Oh, you mean the last white sentence on the board? Work is the accumulated impact of force through space. Wait, so that's such a great question, and you should totally give yourself points for that. But I'm going to say, I, we're friends, and I know you still have to get an exam. I, I hate saying. So the answer is no. I hate saying no. I don't know why. Like it's a great question, but actually no. The sentence can't like like if I said per so Muhammad asked like can I and I think he means this white sentence at the end of the board at the bottom of the board or look.
No, it was actually
Oh,
it
okay.
was actually the yellow sentence. Like after 1 meter of displacement per unit time.
Oh, okay,
But
okay.
but then I started to realize like as you said like because you're kind of like getting into a limit in a way. So limit is like you're kind of shrinking time as you go as well. So I'm like, okay, no, so you can't include it.
Okay, but great. Yes, you're correct. And you definitely should give yourself a million point. And you just used your voice. There's like 14 point portals. You should, and I know I still owe you an exam. I'm so sorry. Okay. But yeah. But it's such a great question because even though the answer like is no, right, it totally demonstrates the why we're making this shift to this other topic. Like if I, so to everybody, it's not just about Muhammad. If I said per unit time, if like I divide, if I, like he just said, then I'd be like shrinking my attention to one moment, and then I'd be back to the old picture. What we're trying to do here, and I'll even, yeah, what we're trying to do here is actually now extend. We're trying to zoom out and say, what if we don't divide by a unit time and we literally just let something get pushed throughout a space? Like, doesn't force sort of build up and accomplish something through that space? Like, we're looking at like the accumulated accomplishment. So we're not going to divide by unit time. But that was a perfectly clarifying thing. Um, um, and 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 we're gonna, for the moment, we're gonna restrict ourselves. Why I have to keep saying small, at least today, why I have to keep saying it's a small unit. I mean, it's enough distance to make a difference, like enough distance, enough meters or centimeters, whatever, that we multiply the newtons by the meters and we get these things called joules. But it's small enough, we're restricting ourselves to, so that the force value, whatever it is, doesn't change through that interval, so that we have a number of 4 of newtons to multiply by the number of meters. Once we let this thing go so that the force value could start wobbling, then we get into that the next homework sheet that you have not done yet, called work done by non-constant forces. And that's where we have to think about limits and calculus and do calculus in the other direction, do an integral, and that's what we will do Wednesday. But right now, right now, I'm just saying, imagine that. So the displacement could be like kilometers. It could be huge as long as it's not so huge that the force starts varying. Okay, so right now we're saying force times displacement. However, there's more details to it. Oops, sorry. Okay, this becomes an important thing that you sort of alluded to in the homework sheet and then sort of alluded to chapters in a book that you don't have. And I apologize. So maybe you looked around the web. I don't know what you did. Um, um, but there's an issue now. Force is a vector. It has magnitude and direction. Displacement is a vector. It has magnitude and direction. I'm suggesting that we're going to multiply these two things together to get this new idea called work. But how does multiplication work once vectors are involved? Good question. So this is a bit of math now. It turns out, and I'm telling everything I'm saying today, whether you, no matter, I remember if as long as you made an attempt on that homework, I can't even remember when it was, as long as you made an attempt on it, right, then you can eventually get all the points. So everything I'm saying right now is the first time I've said it. I'm not assuming you knew what I'm about to say. I'm like teaching you now, even though you tried to figure it out on your own first. Now I'm teaching you. I am saying that when vectors are involved in a math or science context, there's actually 3 different ways that multiplication can be performed. Again, I'm saying this. I'm not assuming that you already knew it. I'm explaining. Okay. There, at any given moment that there's vectors involved, there's three possible ways to multiply. I'm just outlining the three ways right now for the first time. One of these three ways is the way that is involved every single time we calculate work. So I'm just giving you so I'm zooming out for a second to tell you the three ways. The first way is okay. The first way you already know about and you've used, I mean, like, you just might not have thought of it explicitly, but whenever you have a vector, you can always multiply a vector by a scalar. You can always multiply a quantity that has direction and magnitude by a pure magnitude. And whenever you do that, you will just get a new vector. You'll just get a vector of the same direction as the old one, but a different magnitude. This is, in fact, what that handwriting says, there's no way you can read that. What the blue handwriting at the bottom said, there's no way you can read it. Hold on a second. If a vector is represented by an arrow, with length and orientation, when you take an arrow and multiply it by a pure number, what you're getting is a new arrow, an arrow that has the same direction as the old arrow, but is simply scaled up or scaled down. Like if you had the displacement 3 meters to the northeast and you multiply it by 2, you now have 6 meters to the northeast. You've simply brought that arrow to a greater scale or a smaller scale. That's why pure numbers without directions are called scalars. They simply scale up or down pre-existing arrows. So whenever you multiply a vector by a scalar, you just get a new vector, same direction, new magnitude. And that, in a way, like you've always known, you just might not. So that's one way you can do multiplication when vectors are involved. However, what if you have two vectors? That's a little bit more complicated. And you can tell me to go back. I'm looking at the chat if you need me to go back. Um, so option number 2 out of 3 is that a vector, I just want to see how I wrote this. Yeah, a vector can be multiplied by another vector. You can there's a way to multiply one vector by another vector that will produce a scalar. There is such a thing. That is called the scalar product or the dot product. This is the one I want to explain in depth in a minute. Like this is the one that we care about for right now for work. Okay, wait. So I'm going to explain in more depth in a second. I'm just when you multiply one vector by another vector in a manner that produces a scalar, that's called, it's called the scalar product, but we usually use a dot to denote it. I mean, to symbolize it. So it's called the dot product. I'm going to break it down in a minute, but just so that you have the whole picture, the other thing you can do is you can multiply a vector by a vector in a manner that produces a vector. And this, okay, this, I mean, is called the vector product, or more commonly, this is called the cross product. Like we use, an X to denote this. Now, both the dot product and the vector product are both very important in math, very important in physics. We use them both all the time in physics. Let me also say it's a choice. It's not like, it's just like multiplication and division and addition and subtraction. Like in life, we use addition and subtraction all the time. And it's not, and any numbers that you can ever think of could be added or subtracted. Like, you can take the numbers 2 and 3. You could add them and get 5, or you could subtract them and get -1. Like, how do you know which one to do? It totally depends on the context of the situation, right? Like, if I give you $2 and then I give you $3 more, and you want to know how much money you have in your pocket, you add them. But if I give you $2 and you owe me 3, then you subtract. Like, it's total, right? Like, so any operation can be done at any time. You choose the tool that you need to perform the task. Same thing in physics with vectors. Any two vectors you're ever given, depending on what you're interested in, depending on what kind of measurement you're pursuing, you could dot them together or you could cross them together. Both will occur in physics. The cross product very much will become important in physics 204, like it will. But right now, but so that's the big picture, is that there's like these three different choices. But the choice that we're interested in right now, it turns out, whenever you want to calculate the work done by a force acting through a displacement, what we're interested, like the mathematical tool that we use to produce this physical concept, this measurement, is the dot product. So I'm going to expand on that now. Okay. So I don't know, I'm over. So what I'm now going to do is like explain the concept of the dot product of two vectors. Okay, again, this is like a math thing, math tool. And some of you may, especially if you're on an E permit or something like that, depending on whatever math classes you take in the background, this may have come up in a prior math class. It's totally math. However, it's also possible. I know that for whatever reason, I don't know that it necessarily does come up in Calc 1 or Calc 2. John Jay, I don't think so. I'm not assuming you know this. I'm telling it to you. Okay. But it's not hard. Well, I should never say that. It's not as crazy as some things can be. But I'm going to be general now, okay? And then I'm watching the clock, and I'm want to. This is all meant to be related back to your homework, obviously, but in general. Okay. So in general, if you're given two arbitrary vectors, meaning two vectors that have different lengths in different directions. So say you've got two vectors that are A and B, and say that their directions differ by the acute angle theta, right? So I'm drawing them tail. I'm not adding them together. I'm putting them tail to tail to look at a comparison between them. Um, so if the comparison between them, if the way they differ in direction is the acute angle theta, then I'm now going to define the dot product between the two vectors to be. So there's a definition. I'm just declaring. If I want to measure the product of these two vectors in a way that gets rid of direction, that produces an answer that only has size, that does not have direction, then the answer is this. Literally. And I'm assuming. I'm assuming, like, I'm making a explicit point. If I put an arrow over a letter, it means the whole vector, the magnitude and the direction of that quantity. But once I get rid of the arrow, I'm just talking about its magnitude. Like, it's in effect its absolute value, but in a higher dimensional way. So I'm saying if you want the dot product between two vectors, you take the length of one, multiply by the length of the other, and then multiply by the cosine of the angle between them. Now, that's a definition. But so in a way, that's a memorizer. That would be a GDP, a step 3, like in an exam or whatever. Like you could write that, and it's just how we're defining the dot product to be. But I think the definition makes sense, and let me tell you why. Remember from last week, sine super, cosine crappy, or what you like, right? Sine sensible, cosine counterintuitive, right? If you remember that, you tell me in the private chat, in the direct chat, what is the cosine? What is the cosine of 0? And a hint is, if you're like me, even at age 55, what I do in my mind is I ask myself the sine of 0, and then I take the other answer for the cosine, if you know what I mean. Like I always bring it back to sine of 0 in my mind, and then I flip it for cosine. So great, I already see 2 answers, and thank you for making them all private. Awesome. Oh my God. We're like totally learning something here. Yes, I see 1, 2, 3, 4, 5, 6, 7. Okay, one of them is not right, but yeah, all right, great. I see 7 answers, almost all of them right. And yes, and by the way, if you happen to be the person that put the wrong answer in, and it's private, I'm not changing. Remember, there's a portal literally for wrong answers. You can get extra points for the fact that you just had the guts to do something and then happen to be wrong. I'm not kidding, but like, because thank you for like hanging in and taking a risk. But anyway, yes, the answer actually is 1. The cosine of 0 is 1. The sine of 0 is 0. That's what I memorized. The cosine of 0 is 1. Now, why is that relevant to this? Because if you think about it, totally. Thank you. By the way, person who just like acknowledged, like you totally should submit for points. You are totally engaging with me and in the class. So and okay, fine. So you just misheard the question. Totally get it. I don't want to but thank you for hanging in and being honest and staying with the dialogue. You should submit for points, really. And I'm I'm down. Okay, but yes, so we're all on the same page. Cosine of 0 is 1. Now, what that means is I never thought about this before until I did. But that means that cosine really measures how aligned two vectors are, right? Like if you have two vectors and you multiply their lengths together, but then you multiply by the cosine of zero, what you're really saying is that if the two vectors were literally parallel with each other, if the angle was zero, you would multiply by one length, you take one length, multiply by the other, and then multiply by the number one. You would literally get the full, it would act like normal multiplication between numbers. In other words, if the two vectors were aligned, you would treat them just like two numbers on the number line, and you would just get an answer on that same number line. If the two vectors have the same direction, then direction's not playing any role in the whole situation. There's no need to worry about vectors. You just have numbers on a number line on one axis. So if they're if it's two numbers on the same axis, like 3 and 6, you would just multiply them together and get 18 on that axis. It's when the vectors start drifting apart, when the angle between them gets bigger and bigger, that you take a smaller and smaller percentage of their product and spit it out. In other words, if the two vectors are totally perpendicular, if the angle between them is 90 degrees, the cosine of 90 is zero. So no matter how long the two vectors are, you would multiply the length of one by the length of that, and then multiply by zero, you'd get nothing. In other words, what the dot product is doing, well, it says here, it's measuring parallelism. Another way to put it is the dot product allows us to extract a scalar value from the measurement of these two vectors by only multiplying together the extent to which they line up. We're only multiplying. Oops. I'm saying you take the two sides of the vector, you take the two lengths of the vectors, you multiply them together, and then you multiply by this factor, this like percentage that says how parallel they are. The more lined up they are, the higher the percentage of the whole product you take. So I'm saying cosine makes sense because it allows us to get rid of directionality by only looking at the extent to which the two vectors agree on direction. Well, another way to put the same thing is just like tilt the whole situation. Pretend like B was here on the x-axis and A is up here like this, right? Like if you zoom in on A the way we did in prior material, if you zoom in on A and look at A going northeast really means going some amount east and going some amount north, right? The vector A has a vertical component and has a horizontal component. It's hard, or it has an opposite component and has an adjacent component. Its adjacent component is A cosine times the angle. What we're in, and multiplication is commutative. So when I say AB cosine theta, another way you could look at it is I'm really saying like A cosine theta times B. I'm just taking the projection of A onto the axis that B is on and just multiplying that projection by B. It's as though A were a stick in the ground and we're looking at the shadow and we have a light above that stick. So we look at just how much of a shadow A would cast on the horizontal ground, and that shadow would be not as long as A, right? Like the horizontal leg of the white triangle isn't as long as the hypotenuse, but we're just taking that horizontal leg of A and multiplying it by the horizontal vector called B, right? That's what we're doing. We're only multiplying. So bottom line, and I'm moving on, it's 10:15. I'm saying that what the dot product does is it doesn't just multiply two vectors together. It takes the pieces of the two vectors that are lined up. It multiplies parallel components of vectors in order to treat them like they are numbers on one number line, and then it spits out a numerical answer. Now, that's what the dot product does. You might imagine, if you're guessing already in your mind that the cross product would do the opposite, that the cross product would use sine instead of cosine, you're completely correct. Like, you get it. I'm not going there now. I don't need the cross product right now, but yes, you get the picture. What I need now is this thing, so I'll say one more time. Sorry. Okay, so the dot product between two vectors doesn't just multiply the vectors, it multiplies the like components of the vectors, the lined up, the parallel components of the two vectors. That's what the dot product does. Now this, and thereby it produces a scalar amount because it gets rid of the idea of direction. But it does so in like a legal, like a thoughtful way. Now this, I'm just looking at the chat. Wait, sorry. Okay. The this is totally what we want for the concept of work. Well, I'll say this quickly. Okay, just to do a super quick example, and then we're going to get to the homework fine, with 20 minutes left. Just to be clear, say, oh, this is a terrible diagram, but what I'm trying to say is, say we have a block on a table, and we're going to push the block 5 meters across the table. Like we're going to push it horizontally 5 meters across a horizontal table. But we're like a human being. So like we're taller than the box. So the most easy way to push it, just from like a practical standpoint, is instead of kneeling down next to the box, we're going to push at an angle, right? So let's say we're going to push with 20 newtons of force at a 60-degree angle, 60 degrees measured from the horizontal, right? We're just doing that because we're being practical. Well, what would be the work that we would do? What is the work that we're doing on this box? Well, if you zoom into the I'll just try to go up there. Is this what I just said? Yeah. If you zoom in, we're pushing like this at this angle. The push is like a hypotenuse. That means, just like with the whole mg and the mg sine theta and all the business, when we pushing sorry, down at this angle, what we're really doing is pushing over some amount and we're pushing down some amount. Right? We're pushing over an amount p cosine theta. See, and we're, because it's adjacent, and we're pushing down an amount p sine theta. By pushing down on the block, we're not in any way, but the block's entire displacement is horizontal. The amount that we're pushing down the block is not helping the display. It's not contributing in any way directly to the horizontal displacement. In fact, as you learned in like last week, it might even be a bad thing. It might even be contributing to friction or something like that, but it certainly is not directly helping the blocks move forward. All that is actually helping the block move forward is the horizontal component of our push. So the work that we would do on this block would be like p cosine theta times x, or put another way, px cosine theta. Either way, like I'm saying, this would be the definition. We would do the dot product of the two vectors. And what we would get is like 20 cos 60 times 5. Sorry, I'm just going to finish this up here. And cosine of 60 degrees is 1/2. So we would get 500 joules would be the work that we would do on this block. What I'm trying to say very quickly is it wouldn't be 20 times 5. It would be 20 times 1/2 times 5. Because not only some portion of your 20 Newton force is actually contributing to the horizontal displacement. And notice our answer would not be 1,000 joules, and also our answer is not 500 joules in any direction. It's just 500 joules. It's just a scalar amount. That's how it works. So that's a concept of work. Oh, well, that's a concept of a small but finite, like a work done by a constant force. Bottom line, I'm saying in the end of the day, I am saying the definition of work then is a dot product. Well, okay, so in sum so far. A small amount of work is a small but finite amount of displacement vector dotted with a force vector. And what that means for all intents and purposes is this. This is what work is so far. The parallel components of two vectors being multiplied together to get a scalar. That's what it is. We have 15 minutes. I'm just thinking about that for 1 second. All right, I'm going to start. We have 15 minutes. I'm going to start going over this homework then. I mean, there's obviously more to say about this, but let me just get us rolling on the homework. So let me really quickly. So what I want to apply now, obviously there's this thing at the top about kinetic energy. I will get to that next, but right now I'm focused on this idea that it's a dot product. So this problem, a boulder rolls down a ramp, is what I want to apply this to now. You have a boulder rolling down a ramp. It could be a block sliding down a ramp. And we're not worried about friction. There's no mention of friction here. It says so part A, it says calculate the work done by gravity on the boulder as it travels down the ramp. Is this work negative or positive? Okay, there's a lot going on there. Let me first say, I'm going to go a little bit out of order. As far as negative or positive, this is a subtle point that I want to make clear. In fact, it even says it at the top of the sheet. But work is a scalar. It doesn't have direction. By that I mean doesn't point northeast or southwest or forward or backward or anything like that. It's just a number. However, just like temperature, which is also a scalar, work could be negative. Why? Because work is a product between two numbers. Numbers can be negative. Work could be a positive times a positive, or it could be a negative times a negative, or it could be a negative times a positive. In other words, yeah. Um, so what does it mean to say that work could be positive or negative? Just this. Just this. The cosine of the cosine of I'm just questioning whether I should switch the screen. I'm going to switch the screen in a moment. Well, I'll switch the screen right now. I'm talking about Roman numeral 1, part A of the sheet, and where it says, is the work negative or positive? That's what I'm addressing right now. I'm going to switch the screen to address this. Um, so just to be clear, work could be a positive number or a negative number. If it's a positive number, it means that the force and the displacement components are ultimately pointing in the same direction. But if they're in opposite directions, it's the cosine of 180, you can have two vectors that point in opposite directions. The cosine of them would be 180 degrees. You get the cosine of 180 degrees would be -1. So if work is negative, what that means is that the work is failing, in effect. It means that you're pushing one way, but the actual object is displacing the other way. Can that ever happen? Yes, absolutely. For example, friction all the time. It will never happen if only one force is acting. But if more than one force is acting, one force can win over another force. So if I'm pushing a block across a table, I'm succeeding. I'm doing positive work on that block. But friction, meanwhile, is pushing back the other way and it's losing the battle. The friction is pushing. It might even be slowing down the block, but the block is still moving forward. So friction would be doing what we call negative work. Work can be positive or negative. Okay. So now I want to go back to that. So now we have 10 minutes back to that problem. Wait, this is homework 7, I believe. Tell me if I'm wrong, but I believe this is homework 7. Well, anyway, homework
It's
7.
8.
Oh, wait, it's 8 actually. Oh, so then the non-constant is 9 and the gravity one is 10. Okay, thank you. So you have a total of 10 homework? I thought okay, thank you. But the gravity one is the last one for sure. Okay, homework 8. Thank you. Um, so Roman numeral 1, the boulder rolling down, boulder ramp. Okay, the first question it asks is what's the work that gravity does on boulder as it rolls? Okay. Okay. Um, so I need to do the force vector times the displacement, but only the parallel components of each. So let me draw a free body diagram. And apparently there's no friction, right? So this is the free body diagram. Now the boulder is sliding along the plane. Like like we said in the lab, it's sliding along the plane. So it might be helpful for me to do a component free body diagram and remember from the lab that the components look like this. Right? In other words, the work is the to be totally clear. Well, yeah, okay. Let's call X. Say X is the distance along the plane, what the ball's actually doing, right? Then the work does not equal mg times x. Let me just make that clear. The work is not mg times x, right? Because x is like this and mg is like that. You have to multiply parallel components. That's what the whole dot product is saying. So one thing we could say is okay, I can cut to the chase. Like I can do the whole cosine theta thing by definition that we just established. Or since I've already resolved gravity into components in lab 5, I've already decided, oh, the component of gravity that goes along the plane is mg sine theta. Then one option I could say it's mg, that the force of gravity that's relevant here is mg sine theta, and multiply that by x. Right? That would be correct. That's one option that is correct. Mg sine theta times x. I know theta is 33 degrees. I know m is 85 kilograms. I don't know x offhand. Oh, sorry. Yeah. Okay. I don't know x, but I know SOHCAHTOA. And I know what's given in this problem. What's not given is x, but what is given is the height of that ramp. Let's call it h. The 11 meters, right? So I know from SOHCAHTOA, I know that the sine of theta equals opposite over hypotenuse, right? So I know that x equals h over sine theta. Stop me if you're not. Wait, I'm not looking at I'm looking at the sheet, not that. Okay, right. I'm trying to find. Remember the key point here. I know it may be a little. We have 5 minutes left. It might be a little confusing that I'm talking sine now instead of cosine, but I'm doing sine because we've already broken up the vector into its components, and we know the component that is parallel to displacement in this case is the sine of mg, because mg is like funny vertical, blah, like all the lab 5 analysis. So if I'm trying to respect the dot product and just multiply the two components that are parallel, one option is x times mg sine theta. And then I back up and say, well, what is x? X is h over sine theta. from SOHCAHTOA, right? Therefore, thus, one way of seeing the work would be mg sine theta times h over sine theta. And then I'm like, wait, mg times sine theta over, I'm sorry, mg times sine theta times h over sine theta? Well, the sine theta seem to cancel. So does that mean that the work is just mgh? Oh, yes, it is. That's the other option. Like, that's a lot simpler. Why does it make sense? Because mg points straight down, and so does h. What I'm trying to say here, this is actually a deep point. I'm trying to say my whole discussion of the dot product was a way of insisting that if you want to calculate work, you don't just multiply any random force by any random displacement. You multiply the components of the force and displacement that line up. So one thing you could do is take the component of the force that is parallel to the displacement and multiply those. That's what we tried to just do. We did mg sine theta times x. Or you could realize that the equivalent to that is taking the force and multiplying it by the component of displacement that's parallel to the force. In other words, multiplication is commutative. That's why I went through the discussion in the beginning to show that it doesn't matter where you put the cosine. It doesn't matter if you multiply it in the middle or at the end, you're just multiplying by it. Same thing here. If I look at my diagram, it look like this. What was given was theta and h, like and m. Those are what we're given, right? So mg points fully down. H is not how the block displaced, but it is the vertical component of the block's displacement. It is the shadow that the displacement would cast if I pointed a light directly at, at the y-axis. Like, so in other words, since gravity always points down, like the sine thetas will always cancel out. And we can always say from now on, this is the point of this problem, the work done by gravity to push something from a height h down to a height 0 will always be mg, the force of gravity, times simply the height difference undergone by the object, regardless of how it gets there. It doesn't matter if a block goes down an inclined plane or down a curly Q, it goes sideways or back. All that since gravity points entirely vertically, all gravity would ever be multiplied by is the vertical component of an object's displacement. So the work done by gravity on an object is always mgh. In this case, when the block was going down, the boulder's going down, it asked, is the work positive or negative? No matter how you define your axes, no matter how you define up or down, if down is negative, then the displacement is negative and the force is negative. They're in agreement. Gravity is succeeding. This work is positive. The work that gravity does on an object to bring it down is always positive. When an object's going up and gravity's still pulling down, then the work is negative. But so the answer to this question is MGH, positive MGH. Oh, there's something in the chat, but it's time for, sorry. Okay. Sorry, that's yes. Okay. So we'll end there. So that's just number one of the homework. Obviously, we'll move through the homework more on Wednesday, blah, blah, blah. But thank you for your patience. Have a great afternoon.
Thank you.
Thank you. And someone just in the chat, I'm going to repeat. I'm not going to turn off the recording because this might help it, but you can go. But someone asked me a good question in the chat to repeat. But yes, you can go if you got to go. Work would be negative. The work done by gravity would be negative whenever an object is on its way up. Like if you throw a baseball up while the baseball's moving up a height h, it's moving up, but gravity's still pulling down on it. So gravity is doing negative work, negative mgh, while an object is ascending a height h. Then when it starts coming back down again, then gravity is doing positive work. Whenever gravity is succeeding, it's doing positive work. Whenever any force is succeeding, it's doing positive work. Whenever it's failing, it's doing negative work. Does that make have a good wait, so private chat person, does that make I'm gonna stop the recording. Does that okay? I'm gonna stop the oh yeah, oh thank you. Okay, great. All right, I'm stopping the recording if anybody's here for